You're being recorded.
Oh, thank you.
Okay, so Wolff's inequality, a mix of Wolff and Nikolaos.
Well, possibly. All right. So, should I start?
Okay, sure. You start. Yeah, Pavel Mozolyako from Petersburg State University.
Okay. Thanks, Nicola. And so, okay, here, just a sec. Yep. So what I will be talking about is actually the proof of Wolff's inequality, the Wolff part, because of course Wolff's inequality, as Nicola already said, is a partial case of Microworkshop and Witten, and they proved that a bit before Wolff, but alas, he didn't know and invented completely a new proof of his own of one half of this inequality. And I think that what I will be saying would be a sort of a mix of ideas of Wolff and Microworkshop and Witten. So some of which would be from Wolff, his manipulations with functions, and some of which will be probabilistic. I never read the actual paper of Microworkshop and Witten, so I have no idea if that's actually the proof in their paper. Right, so let me write something. And so Nicola, in his introduction, he did everything in Rn. I would prefer to do everything in R1 because, I mean, ideologically, there is absolutely no difference. And it's just at some point I will be moving to the dyadic tree. And basically, Rn can be modeled by trees. And it's so much simpler to just draw a dyadic tree instead of 2 to the n-adic, which is the natural model for Rn. Right, and so what I want to say is this. So let's see. We have some basic interval, which is I naught, which is the interval from 0 to 1, usually, but doesn't really make any difference to take an arbitrary interval. And all of the intervals I will be thinking about would be dyadic. So dyadic interval of rank, let's say k, is something j 2 to the minus k, j plus 1, 2 to the minus k. Let it be semi-open so that they would not intersect. And j is, let's write this, j is between 0 and 2 to the k minus 1. Right. So this is the dyadic interval of rank k, and all of the intervals, again, I will consider they will be dyadic. So pick any number, let's say q, which is greater or equal than 1, and a parameter s, which is between 0 and 1, and these are two strict inequalities on both sides. And Paul, I will write the one-dimensional version of this inequality, of Wolff's inequality, which is like this. So integral from 0 to 1. Here you have sum of I dyadic. At some point, I will just drop mentioning that every I is dyadic just because they will be, but so far I will write it a couple of times. Okay, so and I contains x. So you sum over all dyadic intervals that contain x, and you have mu of y. Oh yeah, mu is a non-negative measure, Borel measure on the unit interval. Why not? And below you have the length, well, the size of the interval to the power of s, and you raise everything to q and integrate with respect to x. And turns out that is, okay, let me actually write a constant here. So c of qs times the same integral, but you put the power q inside. So sum of I dyadic, I contains x, and here you have mu to the power of q. of I, and the size of I you raise to the power QS. That's how it should work. And again, of course, the inverse inequality is quite trivial, just because Q is greater than 1 or equal than 1. And here you have a sort of a reverse Hilbert inequality, which somehow happens on average. And for that matter, this constant C, it blows up when Q goes to infinity for natural reasons, and also when S, the parameter S, goes close to 0 or to 1. And there are some examples to see that, but let's leave it as an exercise. But so far, I think that Q is fixed and S is fixed, and we have this inequality here. Okay, another thing that Nicola already mentioned, that when Q is 1, it's just 1, there is nothing to prove really, because it's a triviality more or less. And if Q is 2, the inequality becomes a bit less trivial, but it still can be done without involving any probability or any non-trivial technique, so to say. You just look at how two intervals, two dyadic intervals, behave with respect to each other, and there you go. It's basically an exercise in computing the geometric series. The problem is, of course, when Q is non-integer or even integer and greater than 2. Because for Q equals 3, you cannot use the same simple argument that works for Q equals 2. Right. So what I will be doing is I will try to prove this inequality here in a slightly more general formulation, which we kind of invented because we wanted to use this Wolff inequality to deal with biparametric capacities at some point. And for that, you would prefer to have a slightly more general formulation for this. So in order to do that, I will introduce a thing which is called logarithmic supermartingale with the deriv d, and it is defined like this. So let delta. So this is not a Laplace operator for some reason, but it is rather a collection of all dyadic intervals of any rank, of all dyadic intervals in the basic interval. And I wanna let's say we have a parameter d, which is greater or equal than 0. And a function phi, which lives on this family of dyadic subintervals and has non-negative values. So I call it logarithmic supermartingale with the deriv d. Phi is log supermartingale with the drift term d. If the following thing happens, so okay, let me write it first. So 1/2 of logarithm of phi plus logarithm of phi minus is smaller or equal than phi y minus d. So what do we have here? We have okay, yeah, this happens for any I in the system D. So what happens here? We have a basic interval I naught. We fix any interval I. So this would be the interval I, and we have its two dyadic sums. Okay. The left one, which is usually called by I minus, and the right one, which is usually called by I plus. So these are two sums of dyadic interval I of the rank of I plus 1. And what's written here in this definition here is basically it tells you that not only the logarithm of phi is a supermartingale because the average over two sums is strictly smaller than the value at the father, but also you have a certain drift term. So you have it's quantifiably small by this parameter d. And well, and one.
Don't you want to have a log on the right hand side?
Yes, of course I want, Sarah. That was a typo.
Thanks.
Yeah, thank you. Otherwise it would be. Yeah, sorry about that. It was a typo. Okay, yeah. So basically, this is just saying that logarithm of phi is supermarchingale with a fixed drift term. Okay, so there's that, and you can move it back by removing logarithms by saying that the product of phi of y plus and phi of y minus is actually smaller than phi of y. And you have an extra power from this drift term here. All right, so what I actually want to show is the following statement. So Wolff for log supermartingales. That is, so assume we have assume that we have logarithmic supermartingale phi, which is let me write it for short, logarithmic supermartingale with strictly positive drift. So the drift term here is strictly positive. And also I would like to have another condition that the jumps of the supermartingale, so the jumps of logarithm of phi are bounded from above. Again, when you remove the logarithms, it will basically mean that the maximum of phi of y plus and phi of y minus are dominated by c times phi y for any I in the dyadic system for some constant c. Again, if you take the logarithm of the right-hand side and of the right-hand side, it basically says that the difference between logarithm of phi y plus and the logarithm of phi y is bounded. Right, then for any q greater than 1, I will still keep it here, and I will write something that is very much that looks very much like Wolff. So the integral of 0 to 1, sum of I that contains x, and here I stop writing that I is dyadic because everything is dyadic. Phi of y, and this is on the power q here, dx is smaller than some constant, which now depends on the parameter q, which is the same q as in the original formulation of Wolff's inequality, and this drift term d. And here you have, you basically expand the series inside. So you write sum of I contains x, phi to the q of I dx here. And this is exactly, looks exactly like the Wolff's inequality that I had above. So this one, only instead of this term here, well, actually, instead of this term here, I write the function phi, which is a logarithmic supermartingale. So it is easy to check, and I will leave it as an exercise that let's okay, exercise that the function phi of I, which is equal to mu of I divided by the length of I to the power of s, is actually LMS, logarithmic supermartingale with the non-negative drift and bounded jumps. It doesn't really depend what kind of measure you have above. As long as the parameter s is strictly between 0 and 1, you will get bounded jumps and strictly positive drift. And actually, if s moves to 1, the drift term can be computed explicitly, and you will see that the drift term tends to 0. And it is important here that in this inequality here that the drift term is strictly positive, because a priori, the constant can and will blow up if the drift term goes to 0. So the constant depends on the drift very much. All right. So this is what I actually want to prove here. And the proof is split into 2 parts. I will try to give a short outline of each one because I don't have that much time, I think. And the first part is actually what Wolff did. So, okay, sorry. Yeah, so we have this inequality here, and how we will deal with it? Well, we will take the left-hand side, and we will try to expand the series. Okay, if q is not integer, we might not be able to do this just yet, but we will, essentially. And, okay, sorry, I have something. Okay. Yeah. Okay. I have problems with my tablet for some reason. Yeah, sorry. All right, and we'll just expand the series on the left-hand side, and we'll see what happens, basically. Another thing, which is a useful remark, I will use many should be 2 actually times later, but if we have a logarithmic supermartingale phi, then its power, it's any non-negative power, phi to the power, let's say, of t, is again LMS. Not that complicated to see because, well, when you take logarithm of this guy, t goes outside the logarithm and everything works. And the drift term is actually multiplied by this term and by this power t. So as long as I don't raise my logarithmic supermartingale to the very small power, because then the drift would go to 0. So as long as I don't do that, I will still have logarithmic supermartingale. And let's say with the drift, let me write it down, Gt, where g is drift here. So a very, very useful somehow remark. Okay, so what do we do next? Well, first of all, we get rid of this Peschian parameter q here because, well, I don't really want to have it. So again, I will just write the left-hand side, integral from 0 to 1, and you have I that contains x, and you have phi y, and everything is raised to the power of q, and you have the dx here. So what do we do? Well, we do the stupid thing and say that, okay, q is strictly greater than 1, and with that, we can do the following. So we can write that q is actually q divided by the integer part of q times the integer part of q, right? It's not exactly complicated. All right, and oh, sorry, maybe I should put this here. Yeah, this one. Yeah, that should be better. Yeah, sorry about that. Right, so this is, I hope, still correct. And what's important that this guy is strictly smaller than 1. Should be strictly smaller than 1. But, well, it's between 1 and 1/2. So this term here is not very large. It's not very small, thankfully. The problem would be if it were very small, but it is not. And then I write, of course, the following trivial estimate, which says, okay, let me write it like this. So far, phi y to the power of q divided by integer part of q plus 1, and everything is raised again to q integer part of q plus 1 dx. And then, now, since this guy is strictly smaller than 1, I can write a very stupid estimate, which is sum of phi side of x, phi to the q plus 1 phi, and we have finally an integer thing here. This is an integer dx. Okay, so far we did nothing really. We just used the trivial estimate. However, what we actually did is we actually managed to replace the possibly non-integer parameter q here by something that is very much integer here. And well, we paid the price by having some extra power q divided by integer part of q plus 1 here. But here comes the good thing is that, as you remember, the remark above, this guy by itself, so phi q divided by integer part of q plus 1 is again LMS. So if we could prove our original inequality for any logarithmic supermartingale with a drift, we could prove the same thing for this guy and vice versa. Again, because this parameter is bounded from above and below. So I might just as well rename phi to the power of q divided by integer part of q plus 1 by phi again. So instead, I would like to so without any loss of generality, it is enough to estimate the integral from 0 to 1 phi of y to the power, well, sorry, phi of k sum, of course, sum I that contains x, and you raise it to some integer power, dx. And this is actually very useful because thankfully now that we have an integer power m here, we can expand. And that's exactly what we do. So we write this is the integral, and you take the sum and you just raise it to the power of n, and you have sum of intervals I1, I2, blah, 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 In that contain the point x. And you have phi of I1 times phi of I2 times phi of In. And that would be dx. So you have the sum, and you have all possible permutations of these intervals. Okay, now we remember that our intervals are dyadic. So in order for a point x to be contained in all these intervals, from I1 to In, we use now the dyadic structure, which means basically that all of these intervals must lie in each other. So they must form a nested sequence. So INs form a nested sequence. This is observation number 1. And observation number 2, well, so you have n intervals which form a nested sequence. They all contain one point x. So how many ways there are to arrange these intervals? Well, I don't know, the number of permutations. The number of permutations of the set of n things, which is finite. So without any loss of generality by multiplying this by some constant, we might assume that this nested sequence is ordered with respect to the indices of these intervals. So without any loss of generality, we might assume that I1 contains I2, contains I3, contains blah, 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 contains In, and this contains point x. Because otherwise you have some other permutations of coefficients, you have many different cases, but the amount of such possibilities is very much finite. So what I mean by this? I mean by this that I can write less or equal. Let me write it in red. Less or equal, and less or equal here. Then some constant, which depends on n. Integral from 0 to 1, sum I1, I2, In, this contains x, phi of I1, phi of in. And this is actually the thing I would like to estimate after all. So, okay, now let me have the following lemma, which is where the Wolff's part, playing around with function ends, and the probabilistic part starts. So, lemma. We call it Wolff's lemma. So fix some delta, some positive delta. Delta actually will be equal to 1 most of the time, so it doesn't really matter, but it works for any positive delta. And n, which is a natural number. Then we actually have the following inequality. Sum for all dyadic intervals of phi, where phi is, of course, logarithmic supermartingale, delta plus m of I times the length of the interval I is actually greater than or equal. Let me see. Yep. With some constant. Okay, I should try the constant here. Then the following guy, sum of I, still the sum for all intervals in delta, and you have phi to the power of delta of I times another sum of all intervals j that lie inside the delta, inside the interval I, and here you have the remaining term, phi n of j times the length of j. Okay, phi is a logarithmic supermartingale. Okay, so let us look at this inequality a bit. So first of all, the inequality is naturally trivial with constant 1, because if you look at this second sum here, so if you look at this sum here, and you just take not all subintervals of I, but only one subinterval, which is the interval I itself. So the sum in particular contains phi to the n of I times length of I. And of course, this would be exactly the left-hand side. However, it contains the sum on the left-hand side, contains many other terms. And for instance, a la Wolff's inequality, so you must have the integral here, so you must have something on average. And again, you must have this sum here, because for any given interval I, if you just fix an interval I, this would be dead wrong. However, if you sum over all dyadic intervals, you can somehow get rid of this, well, you can prove the reverse inequality. And the constant here, C, of course, C depends on delta and then again. And again, as you see, phi to any power is logarithmic supermartingale again. So at some point, I will just assume that most of these parameters are just 1, because it would be a bit simple to do that. Okay, so there's that. And so how do we use this lemma to prove whatever we want to prove? Well, the following way. So assume for a moment that this lemma holds. And let us go back to the quantity here. Well, let me rewrite it. So what we have under the sign of integral, we have sum of I1. Okay, what was the order here? I1 started from I1. I2 contain blah blah blah, contain IN contains X, phi Y1, phi of IN. Okay, so this is what we have under the integral. And now, let me write the integral here and forget about the constant, because we will add it later, and write dx. So assume that what I want to do, I want to basically change the order of summation and the integral. And I want to put the integral to the possibly last term. So when I do that, I will get an extra length of in that goes away. And what we will actually get is the following: sum of I1 contains I2. Sorry. Contains blah 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 contains in phi of I1 times so far phi of in times the length of the smallest interval. And you have all possible nested sums like this. And now, I will use the Wolff's inequality by collapsing the last two terms. Well, maybe I should write the last two terms here. So this is phi of in minus 1. So I will consider this sum here. So this is sum of I1, which I will keep for a while. Okay, and this is in minus 1, and you have sum of in inside in minus 1, and you have phi of I1, phi of in minus 1 here, and you have a phi of in times modulus of in, which now is a bit familiar because we can take this part and collapse it by using the Wolff law. So you can write, and I will forget about constants here, so I will just write like this: smaller, approximately smaller or equal, then sum I1 side I2, side blah 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 side in minus 1, and you have phi of I1, phi of in minus 2, and here you have phi squared of in minus 1. Because we used Wolff's lemma, so by Wolff lemma.
Maybe for the length of in minus 1.
What? Sorry? Yeah, the length. Yeah, of course, the length. Yeah, sorry. With delta is 1 and L is 1. And now we repeat. We take this part here and we use Wolff's lemma with delta. We use Wolff's lemma with delta, which is 1, n is 2, then delta is 1, delta is always 1, n is 3, and so on, by collapsing, always collapsing the last two terms. So eventually, we collapse all of them. Of course, we will acquire some constants, some amount of constants along the way, but it's not exactly a problem because, well, some constant must be present here. So eventually you will get sum of I1, let's say, which is dyadic, and you have phi to the power of n of I1 times the length of I1. And now we take this guy and move it back to the integral form, because again, useful exercise in changing the order of integration and summation just tells you that this is the integral from 0 to 1, phi to the power of n of, sorry, I always forget the sum. Sum for I1 that contains x, which is dyadic, and phi to the n of I1 gx. And this is exactly what we wanted to have on the right-hand side. So essentially, as long as you have Wolff's lemma, there are no problems whatsoever. And So let me recall what the Wolff's lemma is. We want to prove this inequality here. And again, since the power of logarithmic supermartingale is always logarithmic supermartingale itself, we might as well take phi to the m to be our new phi, and then delta will change to something which we don't care about really. And what I want to say is that I will try to sketch a proof of Wolff's lemma for n is 1 and delta is delta. Because as long as we have this, the general case easily follows. And I would prefer to have this distribution of parameters. All right. So that's how it goes. And let me write the inequality once more. So we want to show that some for all dyadic intervals phi to the power of delta plus 1 of pi is bounded with some constant, bounds with some constant. First of all, sum of O to the delta, and you have J, sum of J inside I, and N is just 1 here, times, and here you have J. So this is the inequality we want to show. Now let us remember.
Sorry if I'm so or not. No, there is still a missing length of I.
Yeah, thank you for noticing that. Yeah. Yes. All right. Now, here, what we would like to see is what would be the best case scenario, really. So first of all, these intervals which we sum over have dyadic structure. So we have so for a fixed interval I will represent them as the vertices on a dyadic tree. So you have interval I here, and you have all of its descendants, and you have points J. So you sum over all J's which lie below I, and then you sum over all I's. So this is basically how the structure looks like. And assume for a moment, we really cannot do that, but assume for a moment, let's forget everything about the function phi, and we'll look what would be the best distribution of the values of phi. So assume for a moment that the function phi decays exponentially everywhere. Phi decays exponentially everywhere. We would be very lucky if we had this, but well, why not assume that? So what we would do there? Decays exponentially, I mean, so when you pass from father to child, so let's say from I to, let's say, I minus, your function is multiplied by some constant which is strictly smaller than 1. And is bounded actually from 1. So very, very good scenario. So what would we do then? Well, we would just notice that this sum here, phi of j, so in this case, sum for all j which lies inside I, phi of j times the length of j can be, is actually dominated by the first term, phi of I times the length of I. Because, well, you just sum over all descendants of the fixed rank. Let's call this an exercise. And then we would have nothing to prove, really, because this second sum, which usually is a problem, can be collapsed due to the exponential decay of function phi. Okay, function phi is a logarithmic supermartingale. No, we don't really know if it decays or not. So let us assume a completely different scenario. Phi grows exponentially everywhere. Then, of course, the second sum would be a very nasty thing to handle. But then we take the right-hand side and we change the order of summation. So in this case, we just write that sum of I, phi to the delta of I, sum of j inside I, phi of j times modulus of j is just sum of j, phi of j times modulus of j, and you put the external sum inside, and you have i's that contain j, phi delta of I. And if the function phi grows exponentially, what we have is that the value at the interval j would be the largest one. It would be the last term of geometric series, right? So then that would say, okay, in this case, sum of I that contains j phi delta of I again is smaller or equal by than the last term, the phi of j to the power of delta. Well, if phi grows exponentially, then phi to the delta grows exponentially as well, right? So, and then again, the sum would be something like sum of j by now, phi to the 1 plus delta of j times the length of j, which is again what we want to have, but with j instead of I. All right, so we have two best case scenarios. If phi decays very fast, we are good. If phi grows very fast, we are good. Well, the life is not so accommodating usually. So phi might decay on some trajectories, it might grow on some trajectories, or it might stay the same. But here we remember that phi is actually a logarithmic supermarching game. And what we do, we basically look at the trajectories where phi grows or where phi decays. And it turns out that as long as phi decays fast enough, it is very good. And on most trajectories, phi decays very fast. So heuristics. Phi is a logarithmic supermartingale. So generally, it would follow that on most trajectories, and by trajectory, I mean some path from the root of our dyadic tree to the leaves. So a nested sequence of intervals. So on most trajectories, phi decays actually exponentially fast. So on these trajectories, we are in the situation number one. So what happens on the rest of the trajectories? Well, it may decay not so fast, or it might be stable, or it might grow. So what we do is that we pick up the trajectories where it decays. That would be the most of the trajectories. Then it is good. We pick up the trajectories where it grows exponentially fast. Then we are also good by the virtue of the argument above. And then finally, we have the trajectories where phi doesn't grow too fast or doesn't decay very fast. And again, phi is logarithmic supermartingale. So this amount of trajectories is very small compared to the all possible trajectories. This is a sort of good lambda inequality, basically. Here we use the supermartingale property. And it turns out that on this small amount of trajectories, we don't really care what phi is. And this can be swept under the rug, again, by estimating the stuff. So this is the general idea. And since I have about, by Nicola, how much time do I have? I think I already am talking for like 45 or so minutes.
Yeah, but you cited inequality as an arm? No.
Okay.
I'll say you can take the time you need.
No. Can I take like another 10 minutes? I think.
Yeah.
Okay, great. So I will try to get that. Okay. So this is the general idea. And now let me write down it in a bit more proper way. And let me introduce the following things. So again, I identify the dyadic intervals with the vertices in the tree, and now I will introduce the following sets. So let's given a dyadic interval and a number k, which is non-zero. I define the set A of I k to be the collection of all dyadic intervals that lie inside I, and they might be equal to I, such that the distance, I will say, what the, well, okay, let me write it in a slightly different way. The rank of J minus rank of I is exactly K, and we also have a condition on the growth. So phi of J divided by phi of I is smaller than 1 plus some small number r, which we will pick up much later, to the power k. R is small, to be picked up later. Right, so what does it mean here? Well, it means that in the picture where you have a dyadic tree and an interval I, you go downstairs exactly k steps and consider all the successors J of our dyadic interval I that are on the step k. So the length of J, let me write it this way, you can write it this way, length of J divided by the length of I is 2 to the minus k. This is what we mean. And basically this is the set where of intervals J where the function phi doesn't grow too fast. So you see that you have a smaller equal than 1 plus r to the power of k. So you might have exponential growth, but not very fast growth. And you might have exponential decay. No problem whatsoever here. And also, let me define another set, B, again, of I and k. This is a collection of intervals, J inside I. Again, rank of J minus rank of I is exactly k. But now we have something that is not, we have a different growth condition, or actually decay condition. So we ask for the ratio of phi of J and phi y to be greater than 1 minus r to the power of k. So what I mean is that A are not so fast growing points, well, intervals, well, let me call them vertices, and B are not so fast decaying. So I introduce these two sets, and basically all of the subintervals, the interval I, can be split using these two guys. Also, I write A of I is the union of all k's greater than 0, A of ik, and the same goes for B. B of I is union of all k's greater than 0 of B of ik. So I just take the union for all possible generations. Okay, so now let us take the right-hand side of the Wolff's inequality, and let's see what we can do there. So we say, okay, what we want to estimate again? We want to estimate this guy. So sum of i's, phi to the delta of I, sum of j's inside I, phi of j, length of j. And okay, we say this is sum of I. The first sum still remains the same. And here you have three possibilities. Times sum j inside I, such j is in A of I. Oh, sorry, is not in A of I. Plus sum j in I such that j is not in B of I. Well, let me write it like this, because that would still be true, right? And I have the rest. Sum j inside I, such that j is inside B of I intersected with A of I. So as you see, if you have a point which is below I, if you have an interval which is a descendant of I, it might be not, it might lie in the complement of the set A, it might lie in the complement of the set B, and the other possible scenario when it lies in the intersection of those, right? A and B. And this is actually very good, because what does it mean that it lies in the complement of A? This means very fast growth. What does it mean when it lies in the complement of B? This is very fast decay. And if you have the intersection of B and A, not too many trajectories here. So again, I will leave it as an exercise to say how can you estimate this term and this term here, and I will just deal with the last one, because my time is up, I think. So let me finally say where we will use this guy is the exponential supermarketing game. Well, we are left to estimate the third term, because the first and the second one are quite easy here. So we are left to estimate this guy here, sum of I in the dyadic intervals phi to the delta of I, sum of j, which lies in the intersection of A of I and B of I, phi of j times the length of j. This is what I want to say. Okay. Well, next, of course, I say that this is the first sum again remains the same. And here I finally split it back. So this is sum over all k greater than 0, and sum of j is in AK intersected with bk. Of course, I can do that because for different k's, AK and bk, they don't intersect. They are on the different steps from the interval I, and we have still this guy here. Okay, great. So thankfully, by now we know that now we use the fact that the function phi lies in the set A, so it doesn't grow very fast. So what I'm using here is I'm just writing the estimate. So J lies in AK of I. I'm using that fact, and this is again the first sum, phi to the delta of I, and here I have k is greater than 0, and here I have sum of j is in AK intersected with bk, and here I write 1 plus r to the power of k phi of I. I'm using the definition of the set AK. And here I use J. And I say, okay, it's still small or equal. Then again, I will keep the first sum. Should have thrown this away. And sum of K is greater than 0. And now you see, basically, for every fixed parameter K, what do we have inside this sum here? We have 1 plus R to the power of K. It doesn't depend on J, or on the position of J. It only depends on its relative rank to I. You have phi of I, doesn't depend on J. You have only one thing that depends on J, and this is the Lebesgue measure of the interval J. And of course, if you sum overall Lebesgue measures of the intervals of relative rank K, here you will get exactly the length of I, so which I will be writing here. So you have 1 plus R to the K. Well, not yet, sorry. Yeah, 1 plus R to the K, you have phi of I. You have the size of this set. I will write it like this, and AK intersected with BK. And you have the length of, the total length of J. Great. And again,
what J is 2 to the minus.
Oh yeah.
Length of I, right?
Yeah, just let me just replace it. 2 to the minus K, length of I. Let's write it like this. So what you do, you move this guy up here, you move this guy up here, and you are left with the, so this is sum of I phi to the delta of plus 1 of I times the length of I. So this is what we want to have. And we are left with this series, K greater than 0, 1 plus R to the K, the cardinality of, well, let me write even more, the cardinality of just BK of I. I mean, if I remove this set from the intersection, the cardinality becomes even greater, and 2 to the minus K. Well, what we want to show that this series converges to something that does not depend on the interval I whatsoever. And it is here that we use the logarithmic supermartingale with the strictly positive drift property. Because the final claim there exists an epsilon which depends on the drift G, such that the total amount of points and maybe the parameter R, but it doesn't depend in any meaningful way on the parameter R. The smaller R is, the greater epsilon. So I might as well not include it here. So the cardinality of BK is smaller than 2 of I, sorry. Is smaller than 2 than what? Than 2 to the K times 1 minus epsilon. Irregardless of what the interval I is. So regardless of I. If we know this, then we're done, basically. Because R, now we choose R to be very small. It doesn't mess up with epsilon here. 2 to the minus K is 2 to the minus K, and 2 to the power of K times something strictly smaller than 1 eventually gives you a geometric series, which converges to something that doesn't depend on it. So the only thing would be to check this for a logarithmic supermartingale. And this is pretty much a direct corollary of what is called by Azuma-Hovding inequality, or basically it's a good lambda inequality for supermartingales. And let me recall, and by now, because we can rescale, it doesn't really matter where your interval I lies. So we might as well throw everything away and think that your martingale or logarithmic supermartingale starts with this point. So this is the new root of our tree. and everything that lies below, of course, has a treat structure by itself. So no problems here whatsoever, and let us try to see what this amount of points is, and to see how can we estimate it. Well, what does it mean that J is in BK of I? Again, let us remember that. It means that phi of J divided by phi of I actually is greater than 1 minus r to the k. That's what it means, right? Okay, great. Now let us call big phi to be log of small phi. And well, what does it mean? Well, it means that phi of J minus phi of I is greater than minus 2kr. Because you just take logarithm of left-hand side and on the right-hand side. And on the right-hand side, you get k times logarithm of 1 minus r. This is approximately this. Well, it's not approximately this, it's approximately kr, but if I put 2 here, it will still be correct. So this implies this. And phi by itself is a supermartingale with a strictly positive drift. So what you are asking is to estimate the amount of points where your function phi, where your supermartingale phi does not decay very fast. So phi of J, so here you have I, somewhere deep inside you have J, and whilst you are going from here to here, you don't drop down very fast. But it cannot happen because on average, every time you make this step, you drop down at least by G, by the drift drift parameter G. So on average, the average value of your supermartingale on every step drops down by G. So in K steps, it must drop down by K times G. And if R is taken to be very small, then you are asking for the points where it doesn't drop down by more than K times 2R. So if 2R is much, much smaller than G, then these points are pretty much non-existent. And this is what I want to say. So the statement, the estimate on the size of decay follows from the following lemma. Another lemma about dyadic supermartingales. So let's phi be dyadic supermartingale with a strictly positive drift G, which again means that 1/2 of phi of I plus phi of I minus is smaller than phi of I minus G. And its differences are bounded from above, just from above. So phi of I plus minus phi of I is always smaller than some constant C. This is actually what happens here. Then for any k greater than 0, any r that is smaller, let's say, than G over 10, let us be on the safe side here, then the amount of points G such for any I dyadic such that rank of J minus rank of I is exactly k, and phi of J is greater than minus k times, let's say, 2r here times phi of I is smaller than some constant times 2 to the k 1 minus epsilon, where epsilon is again, as I mentioned, epsilon G and R. So this is exactly what I was just saying. This is the lemma, which immediately implies our estimate. And how do we get it? Well, we get it from finally a version of Azuma-Hövding estimates for a version of Azuma-Hövding inequality for supermartingales with bounded differences, which means that Azuma-Hövding. So let ZN be just a supermartingale with the bounded differences. Zn minus 1 is smaller than Cn. Then the probability of the fact that Zn minus Z0 is greater than some number k is bounded by exponent to the minus k squared. And here you have, it doesn't really matter what you have here, but j from 1 to n, c j squared. Well, maybe some constant here doesn't really matter. So this is a version of good lambda inequality for supermartingales. And if you just take this inequality and we will try to apply to what we have here, we have two differences. First of all, we have drift d, and second of all, our differences are only bounded from above. Well, the second thing is not exactly a problem, because we can redefine our supermartingale by cutting everything, by stopping. Whenever our difference becomes too small, we just stop the martingale and be done with that. And by too small, I mean, let's say 2, doesn't really matter. And the drift, you just rescale this into the driftless version. So instead of small or greater than minus k times 2r, you get greater than k times d minus 2r here, basically. And then you apply Azuma-Hövding, and immediately when you try to compute this guy on the right-hand side, it turns out that it is 2 times k times 2 to the power of k, minus k times something. And this basically, this amount of points is exactly the probability of having these points here. So then the rest is just visual application of good lambda inequality. And after you do that, basically you are done. So to sum it up again, 10 minutes, to sum it up, you just look at the trajectories where your function blows up. They're good, they're nice for us. You look at the trajectories where your function decays. Again, they're good for us. And then on the trajectories where none of that happens, these trajectories are not very numerous. Actually, there is a very small amount of them with respect to the total amount of trajectories. And then we just say, okay, we don't really care about them. Everything will be taken care of by this length of j. So that works for any dyadic logarithmic supermartingale with positive drift, as long as the drift is positive. If the drift is 0, then you can have problems. But drift in our case is never 0, because the drift is exactly, it's 1 minus s times logarithm of 2. So as long as s is strictly smaller than 1, then we are actually good. Okay, so that would be it. Say thanks.
Thanks, Pavel. But then for s is equal to 1, the inequality is false.
Yes. And okay, so you can cook up an example of that, actually a very stupid one. You always move your mass to one of the sides, actually. In this case, you will have infinity both on the right-hand side and on the left-hand side, but this would be two different infinities, so to say.
Yeah, you could also prove it indirectly. If it was true, you get around the theorem about Carlson measures for the hard space.
Yep.
Are there questions? Is there no other questions? Okay, thanks. We just readjust a little bit for Nikos the lights.
Mhm.
And the
Hi, Pavel.
Oh,
Hi, Pavel.
Alessandro.
How you doing?
That's all right. Don't ask, I won't tell. I mean, up until actually the start of this workshop, I was writing another report. I mean, I have written like, I don't know, 10 of them in the last month.
Can you go to the office to work or not?
Well, I'm in the office right now.
Okay.
Which, well, Nikos.
Hi, Pavel. How are you?
Yeah. I guess you heard me.
is it off? Nope. Okay, because okay, last speaker is Nikolaos Chalmoukis from Bologna. We'll be talking around looking how to even
Inequality. Weighted normal inequalities for fractional integrals. Thanks. So probably should start with a disclaimer that I know next to nothing about what I'm talking about. So this is epsilon that I know that I will tell you. And also, we didn't rehearse the talks, so I have quite common things with the talk of Nicola. I mean, I think risk potentials by so far are quite well motivated, but I will start in the beginning in any case. So this theorem that we're going to talk about, probably it should be called something like Hardy, Littlewood, Sobolev, Stein, Weiss, Magenhaupt, Witten theorem. Because all of these people contributed in the final form of this theorem. If I want to change the video camera, Nicola, how do I do it? Start as in top of Nicola, which is with the Laplacian. And you can look at the Laplacian from the Fourier side. I know we've done these calculations already, but so for some sufficiently smooth function f, this is just 4/4 maybe. But if one wants to define some notion of fractional integration, you just have to, instead of put a 2 here, put some negative power. So you can at least formally define this negative power of the Laplacian as the as we saw again before, it's what is called, you can see it as a convolution. Let me use gamma for the order of integration. You can see it as a convolution with this kernel. Very well. So this Markenhaupt-Witten theorem, in fact, what it does, it studies a quite natural question. So when this integral operator is bounded from LP to some LQ. And even more when you have some weighted norm inequalities of this type. So here you can put some weight function W, and you can so for which weight functions and for which P and Q you have such weighted estimates. So in fact, one can, for these risk potentials, they satisfy the following homogeneity property. So if you find this dilation operator, you can see that if you conjugate the dilation, then this is just and you just do a change of variables, and you see that this is delta to minus gamma, the risk potential of that. That's the change of variables. So what this tells us is that if we hope to get such an LP and Q estimate, and P and Q cannot be arbitrary. In fact, if you have so take some F compact support, for example, and you take this is a keyword, this is keyword, but this delta comes out in the denominator as delta to n minus n over p. And in the denominator, we have, you can write this as t delta, this one, t delta. And this we saw before that it gives you a delta to the minus gamma. here delta 2 minus n over q, and here you have just something which is not dilating. So, but still, by letting delta go to 0 and infinity, we can see that minus n over q minus gamma plus n over t to be 0. This gives you exactly that 1 over t equals 1 over 2 minus gamma over n. Okay, so we should study boundedness properties of the risk potential when P and Q satisfy this relation. So now, let me talk a little bit about the history of this problem and why I claim that all these mathematicians contribute in developing this theory. So first, you have Hardy Lewis in 28, the following theory. When n equals 1, where they deal with the case n equals 1, some fractional of the integration, and then the weight function is just 1. They prove that you have this, the boundedness of the operator, for p strictly between 1 and infinity, and you have some type of weak estimate. So the measure of the set where this vector is started on lambda, we want a constant, this one norm of f by lambda for p equals 1. Then you have Sobolev in 38, 10 years later, that he proves the same theory for all dimensions. Then, even later, you have Stein and Weiss, that they prove the same theory, but for a weight function where is like this? Yeah. In 58, that they prove the same theory when this weight function is from x to the sum. And then finally you have something called Middle 74, that they characterize exactly all measures that all weights W that satisfy this inequality. And they are the so-called AP weights. So let me state that in fact the Markov-Witten theorem gives also some more information, and that I'm going to tell you about now. And in this more information, it produces a fractional maximal function. And in this maximal function, it's hidden inside this inequality by Wolff. So let's do things one. So now we are talking only about the Markov-Witten theorem because it includes all other statements. So again, given, it says that we can split into two parts. First part, it says suppose we have a weight. It means that I start with two definitions. Sorry. I start with infinity weights and the fractional maximum. Infinity weights. So a weight function which is locally integrated is called infinity weight for all epsilon positive, and there exists some delta positive, such that if I have a cube in Rn and some measurable set inside the cube, such that the measure of P is delta smaller than delta times the volume of the cube, then the measure of phi with respect to W, so the integral of W on E is smaller than epsilon times the measure of the cube with respect to W. So somehow you can control the proportion of the mass that stays in E. You can control the Lebesgue measure of E inside the cube. So these are infinity ways, and then we have this maximal function that I talked about before. So suppose f is some positive locally integrable function, then we can find the maximal function of order gamma at x as a supremum over all cubes. This is a centered maximal function. You can do the same with an uncentered one. Let's work up in the middle. So the center of the cube is x, and you just calculate this. This other type of patterns with that. So in fact, the theorem of there are two parts of the theorem. The first, which says that the maximal function that the norm of the least potential, the Q norm, is bounded by the Q norm of the maximal function. And in the second step, you prove that the maximal function is bounded on the splittable LP and Q spaces. So the statement is like this: if W is infinity, then the norm of I and Q is bounded by a constant the Q norm of the maximum. And this is the part which includes also the Wolff inequality. And then the second part is that if in fact the weight satisfies a somehow stronger condition, which is called AP, I write it in a moment, but we will not focus very much on this condition. this talk. Then the maximal function is bounded on the LP point. But I had time, so I thought that it would be interesting somehow to dig in a bit more deeper in the proof of this first statement, since this is a workshop for the work inequality, and since this implies Wolff's inequality, maybe it's not. And this in its turn is based on a good lambda inequality, which I will try to prove in some detail. So I will leave the statement that we want to prove. I don't know, Nicola, who made the observation that this implies Wolff's inequality? Was it?
Good question. When I told Weaver, oh, you're in a political place, what's the he said, no, why? So it was not Weaver.
Okay. Well, so we want to prove a good lambda inequality. What is this good lambda inequality? Is the following. Let me write NW for the measure associated with lambda. So, I started at 5, right?
Yeah.
And we want to prove the following with lambda inequality, that for there exists some constant d that depends essentially only on the dimension and on the order of the relation. So you can think of it as some absolute constant that will not change. Such that if I take any d more than big d, some beta bigger than this d, any alpha positive, I have the following, that the W measure of the set on which T gamma of F is greater than A times B, and at the same time, the fractional maximal function is smaller than A times B. This is bounded by 1/2 d to the minus q, the measure where A gamma, so T is I, is the risk potential. The set, the W measure of the set where this is greater than I. So in fact, aside some small complications, this can quite easily imply this inequality just by essentially the distribution expression. If you integrate here, we make the change of variables, this beta comes out as beta to minus 2, and the right hand side is absorbed in the left hand side. It's a bit technical because you want to know that these things are local integrals and so on, but I mean, the real mathematics is not in probability the lambda inequality implies the normal inequality. The really interesting part is how to prove this good lambda inequality. So, as it's quite common, The idea is the following: that this you decompose this set in some disjoint cubes by some stopping time argument, and then you prove this inequality for each cube separately, and then you sum up. This is the idea. So this preliminary lemma I'm going to write about is exactly this Woodland inequality localized at its cube. So mostly to follow, to be consistent with notation. So suppose again gamma and before, then we can find some beta alpha positive constants depending on the fixed parameters, such that for alpha positive, E positive, and B bigger than D. And for F, a positive measure of function. Q, a cube, such that there exists some point S in the cube where there is potential smaller than alpha. Then, if you define E to be the set, the elements, the points in Q where both this is bigger than AB, and the maximum function is small. Then the measure of T is smaller than this K that we found times E divided by T, some number of constants times the measure. So this is the
So let's say that if there is potential is small.
If there exists a point in this Q where this is potentially small, then you have this version of the good lambda inequality for the Q. Okay.
Nico,
Yes.
can you shift the camera slightly on the right because it's slightly cut? Yes.
Okay. So let's draw it. You have this box Q here, where there exists some point S inside here where there is potential is small. Then the first step is to double this box and consider the constant restricted on this box with double to Q. I mean, is the length of the side is double the length of this side, but the center is the same. Okay, so suppose we can assume that there exists some T in Q where this happens, otherwise the set is empty. So this is some T here. So because we work with centered boxes, I still have to take another box, which is 3 times the length of Q, and is centered at T. I will call this box P. And then you do the following. The interesting thing here is that, in fact, to prove this with lambda inequality, you use already the unweighted version of this Hardy-Sobolev theory. In fact, using the weak boundedness provided by this theorem of Hardy-Sobolev, you can conclude that this set has measured, the back measure, smaller than a constant times AB is my lambda in this case, times L1 normal. Here we have it. But okay. This is just the cutoff of f at the box 2 times 2. So it's just f restricted on this box. Okay, so this is just what you said before. You can put p, which is a slightly bigger box, just to create this maximal function. You just multiply and divide by the length of p to the right power. So that would be p 1 times the yes. So now you can, as we have a maximal function, you can dominate this by the maximal function at t, which is the center of p. And the length of p is just some constant, the length of 3 times the length. So we have the volume of 2 to the same power. But we assumed that this is less than alpha, less than alpha p. To this power. So this is our principal estimate because let me erase this. Let me write that this directly implies. Yes, we have that estimate from the unweighted case. So we just plug this estimate inside here. So we have constant times A goes away, it remains B by P to the power n divided by n times gamma. And times the volume of 2. So we can erase that over there. So now suppose that remember that S is this point where we assumed that F is smaller than alpha. if you have, suppose now you have some point x inside outside 2 times q. So then this distance here is bounded below by so if you have some point y here, then this distance is comparable to this distance here. When your x is outside times q. So in fact, we have that. Just follow the notation with the okay, which is smaller than from L. So if you now take I gamma of h, which is what remains since I have subtracted this this g from f. So it's just the restriction of f outside the box to q. If at this point at x, then so here I'm in the complement. So in the complement, this distance can be dominated by that. Yes.
This one is y. To the denominator, right? And that's less equivalent.
And that's less equivalent. I is less equivalent and A from the hypothesis. So in fact we are done because if I have an x in Q such that the risk potential is greater than AB and the maximum function is smaller than A times B, then this is just the sum of the risk potentials of the two functions, where I can decompose F. And if no, if B is large enough, if B is large enough, then this I gamma H is smaller than AB. If I choose B to be bigger than L. So in fact, this implies that the other half must be bigger than A. So we are in the previous case that we have. So in fact, the set of this x that this happens is a subset of the x that this happens. So we have an estimate for the Lebesgue measure of this set, which gives us directly the Lebesgue estimate for this set or this happens. And this is what we wanted to do. In fact, This is a small lemma, and now to prove the good lambda inequality is just a right choice of constants, a large number of constants. Just I have 4 minutes. I can do. The technical part was only this one. It's interesting to notice that in fact it is used the previous theorem where you have the unweighted estimate. This would land in the quality. Somehow it's not really different. Let me write everything. So we had okay. I write very shortly what we had before. Under the hypothesis that there is a point this is alpha, then some constant in the we want to prove the good lambda inequality, which is so I have a bunch of constants to control, and I do it in the following way. So first, I decompose this in a disjoint union of dyadic cubes, disjoint interiors are disjoint. So this requires dyadic cubes such that there exists some SI in what times this cube where this maximal function is smaller than now. This you can do by some classical stopping time argument. And then I choose my constant as follows, because remember that now I have also the weight W. It would be a little bit easier if I had that process. So I choose beta to be greater than this constant, so that my lemma works. This is suppose it's greater than 1. Remember the epsilon delta definition of the infinity condition. So now I choose epsilon to be what I want to do. But I want to have in the right hand side of my inequality. Suppose that I choose I get some delta from the infinity condition, and I choose D such that I have this equality. So this is the equation that defines D. And I mean, now I have EJ, the subset of Q 4 times Y, that this happens. So this is let's write it again. So yeah, EJ is a EI is a subset of QI where this condition happens. By the previous lemma, since I have an SI in this box where this happens, the norm, the measure of I is less than kappa times 2i b. And so the way I chose delta, this is smaller than delta 2. And then I sum. Then I use a infinite condition, which tells me that the measure W is smaller than epsilon, or the measure W is twice. Epsilon is exactly this constant that I want, and then I sum up together and come to it. That was it. I don't know if you want to technical.
Okay. Thank you.
Are there any questions?
If there are questions, you should read them. Okay, well, thanks to all for participating. And maybe okay. When some of you want to organize a workshop on some other inequality or something, we do it. Especially thanks to Christiana, Pavel, and Nikos. And okay.
Thanks to you for the invitation.
Okay, no, thanks for the wonderful.
Thanks, Nicola.
Okay, I have to go because I have an exam in a few minutes. I have I have the last exam of this session. Okay, I hope to see you soon. Okay, bye.
Okay.
Bye.
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 Ciao, Nicola.